Okay, last set of problems here, 15 through 18, and then we'll be done with this review packet. All right, number 15. Don't stress out over this one. We haven't done one like this, and it won't be on your test. But 15, a health fitness research group wishes to estimate the mean amount of time in hours that members of a fitness center spend each week exercising at the center. They want to estimate the mean with a margin of error 0.5 hours with a 95% level of confidence. Previous data suggests that the population standard deviation is 2.2, which the following is the smallest sample size that meets these criteria. So let's talk about what the margin of error is. So we have this point estimate. Anytime we're doing a interval, it's always going to be x bar plus or minus what we usually say t star times s of x over the square root of n. Now the part that's the margin of error is this part right here. And we want that to be, we want to estimate the mean within a margin of error of 0.5 hours. So we don't really want that to be more than 0.5 hours. So I'm going to set up an inequality. I'm just going to make an equation actually, t star multiplied by s of x over the square root of n. And we want that to be approximately 0.5, 0.5. Now here's the thing. We actually don't know, we're not going to be able to do this with t star because t star depends on the sample size. Because we happen to know the population standard deviation, it's okay to, in this case, to use z star. And that makes things a lot easier because z stars are always going to be the same value with that confidence level. So I'm going to go ahead and change that to z star. And then of course we know that this is 2.2, so 2.2 divided by the square root of n. And we want that to be approximately 0.5. So I'm going to go to table B for a moment. Because remember that at the bottom of table B, your z stars are actually all down here. So that 95% confident, your number that's going to represent z star at 95% is where the infinity symbol is. So we're talking about 1.96 there. I have that number, so I'm going to say 1.96 times 2.2 over the square root of n, and that's going to be approximately 0.5. And I'm going to get kind of lazy here, and I'm just going to plug in my answer choices until I get the one that's closest. So I'll start smallest to largest and work my way in there. So let's start with 60. So 1.96 times 2.2 divided by the square root of 60. And that's 56%. That's a higher margin of error than I want. So I'm going to go ahead and scroll up there and change that to the next number, which is 75. And that looks like what we need it to be. So 75 is going to be the smallest number I can use, or yeah, to get away with getting that within 50%. So just plug in your numbers and you're going to get 75. All right, 16. You have sampled 25 students to find the mean SAT scores at Morris Knowles High School. A 95% confidence interval for the mean SAT score is 900 to 1100, which of the following statements gives a valid interpretation of this confidence level. Confidence level means if you were to do this type of sampling many, many times, you would expect this many percent of the intervals to capture the true parameter. So in this case here, since I'm doing a 95%, I would expect 95% of my intervals produced to capture the true, in this case, mean SAT score. So letter A, 95% of the 25 students have a mean score between 900 and 1100. That's not answering level. 95% of the population of all Morris Knowles have score between 900 and 1100. Nope. If the procedure were repeated many times, 95% of the resulting confidence intervals would contain the true mean SAT score at Morris Knowles. There you go. Number 16 or 17. A 90% confidence interval for a population mean is determined to be 800 to 900. If the confidence is increased to 95%, while the sample statistics and sample size remain the same, the confidence interval from mu becomes, well, higher confidence. Higher confidence, then the bigger your critical value is, the wider your interval is going to be. So it's going to be a wider interval. You're more confident that something is in that interval, but as a result, your interval becomes wider. Last question. In constructing a confidence interval based on a large sample to estimate the mean with a known standard deviation, which of the following does not affect the width of the confidence interval? The thing that does not affect the width of a confidence interval, let's go back to here, X bar plus or minus, I don't care if you use Z or T, but let's just put T star for a moment. The width of the confidence interval, the sample size will affect the confidence interval. So I plug in a number here. The bigger that number, the narrower that's going to be. The standard deviation also affects the width of that confidence interval because the margin of error is all this stuff here. So all this stuff is going to be changed to confidence level. Will affect your critical value, whether that's Z or T, doesn't matter. Confidence level will affect it. The only thing that does not affect the width, this margin of error is going to determine how wide it is. This is your point estimate. That doesn't affect your width. That's just where your starting point. So, you know, if you have that mean of like 100 and your margin of error is 20, then your interval is from 80 to 120. But if your mean is 50 and your margin of error is still 20, right, then that width is going to be the same. So the sample mean has no impact on the width of the confidence interval. Guys, thanks for watching my videos. Hopefully that was helpful. Good luck on your test.